And it had been understood that on 7th August of 2027, it would have an encounter with the Earth. And this is a projection on the B-plane of that encounter of the uncertainty region, of which Andrea Milani has spoken about, so you know all of it. And so this is useful to fix some ideas. As you see, the uncertainty region mapped onto the B-plane is a very elongated ellipse. In this case, it's 1.6 million kilometers long and 1,200 kilometers wide. So the ratio is over 1,000 between the two axes of the ellipse. The missed distance is about 37,000 kilometers. So this is a case very similar to the case that Andrea had discussed of 1997 XF11. That is, no collision is possible at that time with the Earth. Why? Because the Earth is many sigmas away, basically. So it's incompatible. A trajectory that would lead to a collision at that epoch is strongly incompatible with the observational record. And the same plot done a few days later, just 1 week later, shows what happens by continuing to add observations. You are increasing the available information, so the uncertainty region shrinks in space, in the space of elements, and consequently the ellipse on the B-plane shrinks and now goes down to 1.3 million kilometers long, and it was 1,200 kilometers wide, and now it's only 1,000 kilometers. And you also notice that with respect to the Earth, the nominal position, the most likely point of passage through this plane, as written there, can shift back and forth by some point. When Chodas was producing these plots, he was doing that because he had in mind, as we had in mind, the keyhole problem. And actually he invented the word keyhole, which one can define as a small region of the B-plane of a specific close encounter of an asteroid with the Earth, such that if the asteroid passes through the keyhole, then it will hit the planet or have a very close encounter with it as a subsequent return. Okay? And now let's go back to the figure with the 130 days arc. And on that figure, he also plotted a number of keyholes. You see the Earth, the ellipse of the which is the projection of the confidence region, and then you see that there are a few red dots with dates, years marked beside, and these are the keyholes corresponding to the possibility of impacting the Earth in 2046, 2044, if I read well. And you also notice that beyond the edge of the region allowed by the observation, there is a keyhole for 2034, which is not allowed anymore. It means that to hit the Earth in 2034, the asteroid should be on a real orbit that is more than 3 sigmas away from the current, from what the current data, current at that time permitted. And this figure, I think, nicely illustrates all of the game of impact monitoring, because what basically happens is when you discover, as Andrea has already underlined, when you just discovered an asteroid, you have a very large confidence region, so its footprint on the B-plane of the first encounter will be enormous. And being enormous, it means that there could be lots of keyholes inside it, or even direct collisions. And then the game is to add observations, because basically the picture won't change very much, except the fact that the region will shrink, and the game is over when all the keyholes have been eliminated, so to speak. That's how it works. And it works, in fact, in most cases. Another interesting thing for which I use the plots of Chodas is that also for that asteroid, he marked 2 keyholes. He made an enlargement of his figure, and he marked 2 keyholes which actually didn't correspond to a real collision with the Earth, but just a very, very close passage, almost grazing the surface. And these two keels were both for the year 2040, but you see the actual dots are Monte Carlo points of the actual integration. The dots correspond to actual integrations. And he marked two lines inclined with respect to each other, in which the same phenomenon seemed to take place. And he presented this as an interesting new result, not knowing that at the same time we knew the explanation, having arrived to it to a different route. And I will try to describe it. So let's go back now. Now that I have tried to explain you what it is for, unfortunately I have to discuss some geometry, some little formulae. And so let's start by expressing, let us suppose that we have an asteroid whose semi-major, of which the semi-major axis of the orbit is A, eccentricity E, inclination I, somewhere, yes. Capital omega is the longitude of ascending node, small omega is the argument of perihelion. And let's say that we are considering it at time t star, and so its true anomaly will be f star. And we can always write like that, express its position in space in polar coordinates, the heliocentric radius, longitude, and latitude. The longitude is written in this strange way in order not to have ambiguities with the coordinate. Now, very simple definition. It is possible to have a close encounter between a planet orbiting the Sun on a circular orbit of radius AP in the reference plane that is located at that time at longitude lambda p, if, only if, these three quantities, delta r minus AP, over AP, which is the expression before minus 1, the difference of the longitudes, and the latitude of the small body are all small quantities. Small, you can take that as meaning that you disregard the square or whatever you have in mind. Now, when does this happen in practice? In practice, there are two main types of situations in which this happens. This happens if the small body orbit is inclined, substantially inclined, let's say more than half a degree, more than 1 degree with respect to the ecliptic, then in practice, a close encounter with the Earth will take place only if both the Earth and the asteroid are close to one of the 2 points in which the asteroid crosses the ecliptic. Okay? And this point must be also close to the orbit of the Earth, otherwise no encounter is possible. Otherwise, if the sign of the inclination is very small, let's say 100 of a radians, so half a degree, then you can have the situation in which the close encounter takes place not close to one of the nodes, but when the small body, the heliocentric distance of the small body is equal to 1, the heliocentric distance of the planet, and the small body passes either above or below the planet. Okay? And the node can be 90 degrees away. Okay? If in practice this happens, for instance, a famous case is asteroid 2000. That regularly encounters the Earth, as even recently, the inclination is half a degree, and the node is 50 degrees away from the point in which it encounters the Earth. So, now, to describe the encounter, we establish an XYZ frame centered on the planet. We put the Sun on the negative x-axis, so the don't forget that the planet is taken to be on a circular orbit, as I said before, for this setup. So the y-axis in the direction of the motion of the planet about the Sun, and the z-axis is parallel to the angular momentum vector of the planet. We take the radius of the orbit of the planet as unit of length. The unit of time is such that the orbital period of the planet is 2 pi. So in fact, the modulus of the orbit of the planet, we take it equal to 1, and in doing so, we ignore the contribution of the mass of the planet to its orbital speed. This is just to simplify the formula, which otherwise carry some unnecessary factors that don't change. Given the level of approximation of the theory, don't make such a difference. So, having established this reference frame, a possible definition for the coordinates of the small body at time t star could be this one. We take the difference of the longitude as coordinate x, radial distance from the sun, from the planet in this case, because we have subtracted one. The difference of the longitudes as y distance, and along z the latitude, okay, in units of. But in reality, since we have already said that we are only considering close encounters, well then cos beta is 1, cos delta lambda is basically 1, and sin beta stays the same. So in practice, we can keep only the first order terms, and so we have these simplified expressions. Okay. Furthermore, since we want to have a fully analytic theory in which we have explicit solutions for everything we compute, we don't want to have to do a numerical integration to have the outcome of an encounter, we make some further simplification. So we consider that when moving near the planet, the small body, until it crosses the B plane, is moving on a straight line with constant velocity. And we take this straight line to be the incoming asymptote of the planetocentric hyperbolic orbit. And the constant velocity will be the velocity at infinity. Then, in order to have something explicitly computable, what do? We take the instant at which the small body traveling at constant speed along this straight line crosses the B plane, and at that moment we apply the rotation to the outgoing asymptote of the hyperbola. So something that in reality takes place in 3D in space, we do it in one point and in one instant in time. All this works basically if the encounter is relatively close. And of course, if you so the best way to judge this is to consider that the Earth is such a mass, the mass of the Earth is such that you have a close encounter only when the small body passes to a distance from the Earth of the order of less than 1/100th of an astronomical unit. Okay, which means also that this distance is traveled by the Earth in something of the order of the day, or several days at most, which means 1 degree along its orbit. So the velocity of the Earth doesn't turn very much. And this is the justification of introducing something instantaneous. In reality, it takes some time, but this time is short compared to the orbital period of the Earth, which is 360 something days. So we can, having done all these simplifications, before the B plane crossing, the motion, let us assume that the time t star is before B plane crossing. But anyway, we can write this formula in any case, whatever the instant we take, as long as the planet is close. So it is the motion is described by the equations of the uniform rectilinear motion. Okay, and since we are in this XYZ frame, we will have 3 components of velocity that we call ux, uy, uz. And it is customary after Ötvik to introduce 2 angles and the modulus of the velocity vector u. The 2 angles I will illustrate in a moment. So we have these 3 components of the velocity. Now, yes, these are the formulae that tie all these quantities to the orbital elements. So you see that planetocentric velocity is square root of 3 minus a familiar expression. This is the expression of the so-called Tisserand parameter in planetary dynamics, okay, which is an approximation of the Jacobi constant. And then we have 2 angles, theta and phi, that I am going to describe in a moment. theta is between 0 and 180 degrees, and there's this simple expression as a function of u and the same major axis of the small body. And phi is a slightly more complicated expression, and this term here takes care of the sign, but let me not discuss this, it's just boring. So the geometric setup is this one. We have our x, y, z reference frame. The planet is on the negative x-axis, so the y-axis is the direction of the motion of the planet. U is the vector we are speaking, so its magnitude is u. And the angle theta is nothing else than the angle between the y-axis and the vector u. And the phi angle is the angle between the plane zy and the plane yu. Okay? And from the fact that you have to give a sign to the sine and the cosine of phi comes from the fact that in practice, suppose you are encountering the Earth at the ascending node, okay, of the small body orbit. Let's think of an encounter close to a node. Then it means that the z component of the velocity is positive. So uz must be positive, and the cosine phi, in fact, the sign must be positive. How can we make it positive? Just by taking the cosine of the argument of the latitude and divide it by its modulus. And a similar reasoning is applicable for the sine of phi, because let's suppose that our small body is encountering the planet coming from the perihelion, so it's going outward. So the z component, since the x component, since the sun is on the negative x-axis, must be positive. And when does this happen? This happens when the sine f over its modulus is positive. Okay, so in this way, you have fixed all the quantities we are interested in. Now, all this is a little dry, so I am trying now to explain this to you using a figure that was mentioned yesterday by Andrea in relation to a question that was posed, because let's recapitulate what we have discussed so far in terms of actual bodies passing close to the Earth. Okay? Again, don't forget that we are speaking of an Earth on a circular orbit. And the question is, how do we see the small asteroids that are coming to hit us in the last moment of their trajectory? If we discover them only a few days before the hit. Why am I considering this? Because, well, it's improbable that we will be hit by a 1 kilometer asteroid in the next few centuries, because there are not so many of them. Of course, it can happen tomorrow, but the probability is very low. On the other hand, what is frequently happening is that smaller asteroids of the size of this room are falling on the Earth quite frequently. If you think that basically every year we have an explosion in the atmosphere of the order of the Hiroshima bomb, 15 kilotons, and every month we have an episode in which about 1 kiloton is liberated. Nobody sees this, almost nobody, because as Andrea also was describing, there are 2 actual cases in which such asteroids have been spotted just before. Now, since they are small, they are spotted when they are very close to the Earth. Okay? They are exactly in the situation we have described. Now, think, again, make another shift and think when you go out in the summer and look for the for meteors in the first half of August. Okay, what in Italian is called the lacrime of San Lorenzo. The St. Lawrence tears in English, I think, the Perseids. What are these? These are grains of sand which are detached from a comet, Swift-Apple in that case, that are hitting the atmosphere of the Earth, and we see them as emanating from a specific point in the sky. In fact, they are called Perseids because this point in the sky is a small region, let's say 2 degrees by 2 degrees, in the constellation of Perseus. But we don't see them there. We see them all over the sky, but if we trace back their trajectories, they all go back to that point. Why? This is a perspective effect. It's the same thing when you are driving in the rain in the night and you see the drops of rain coming towards you. They are all parallel. They have a certain emanation point from which they emanate, and then there is a parallactic effect by which they seem to open in front of you. So, in the case of the trajectory of a body that is coming close to the Earth and falling on you, what would be the situation? Okay, let's build an image of the sky. This is an image of the sky, abstract image of the sky, is not an actual one, which is centered on the opposition point. This horizontal line corresponds to the plane of the ecliptic, okay? And this is the point that is in the opposite direction with respect to the sun. And the sun is either here or in both places according to your taste. So this is in a rotating frame. And why is it useful to plot it in this way? Well, because of course this is the northern hemisphere, this is the southern hemisphere with respect to the ecliptic, and then this is the night hemisphere, whatever is inside this, and the part of the plot that is outside two lines like that is in the day. Okay? Now, if you take the orbits of all potential impactors, you can build the quantities I was describing before. And this, in fact, the points that you see in this plot have been taken from a population of impactors, not actual impactors. This is a model population that is used to do such simulations. And taking those values of A, E, and I, you construct the phi, theta and phi values that correspond to the direction from which you would see the meteors associated with these asteroids emanate if they were falling on us. In other words, these are the places in the sky where to look for, let's say, this asteroid falling on the Earth just 1 or 2 days or 3 days before the fall. Okay? And the distribution, you immediately notice that the distribution of these points is not even on the celestial sphere. You can also trace these two lines, as was done for this paper. These two lines border a region that is 40 degrees from the sun. No telescope on Earth can look that close to the sun. And so you see that a fracture, actually in practice the limit is worse. I would say that it's around there, 60 or 80 degrees from the sun. So everything that comes from the sun is either there or there, whereas everything that is inside this part could be spotted in principle before fall. Of course, currently we are not covering all of that, and in fact the FlyEye project, which was mentioned by Andrea and somebody else, I think, in the past days, is just aimed at covering such a large fraction in the sky. All this long introduction that I've done is just to tell you that the angle from the opposition point, it is the most favorable point because it's the darkest of the night, is nothing else than sin theta sin phi. Okay, so it's very simple to build this figure, even the orbital parameters. And on the other hand, once you have built this figure, supposing that the original population, the model population, is correct, then you have a lot of information about where the potential colliders come from. So, let's continue. One important point that I would like to underline is that I have introduced the coordinate system without specifying what is this time T star. In practice, I just said that it must be a time at which the small body is close to the planet. In practice, if we want to use the theory for things like building the keels or things like that, we have to do some further constraint. And basically there are three constraints that we can impose, and we can choose one of them. For instance, as was done in the original paper we did in 2003, you can impose that T star is the time at which the ecliptic is crossed. If you do that, you are setting Z equal to 0. The expression for X and Y becomes simpler. And okay, or you can decide that T star is the time at which the longitude, the heliocentric longitude of the small body and that of the planet are equal, which would mean to put Y equal to 0. Or the third possibility, which is the one that I currently like most, is to set the radial distance equal to 1, because in that case X is equal to 0, and you have the other expression for the other two coordinates. And this is a case that this is basically a definition that works in practical cases. So in 2003 we made another choice because we are new to the problem, I must say. So up to now I have explained to you how you go from orbital elements to the coordinates and velocities in this reference frame, but then in reality to exploit the full power of Epic's theory, you have to use all Epic variables. So I have already introduced u, theta, and phi, and I have not yet introduced the rest of the variables which are introduced in 2003 paper, but still we have something still to do. We have to be able to go back to the original orbital parameters. Why do we have to do that? Because the Epic theory will give us some information using Epic variables. So we will have the post-encounter situation described in terms of Epic variables. To be useful, we have to be able to go back to elements, otherwise we have not completed the job. And so, and in doing so, we also can put some attention on the fact that each specific orbital element is tied to one of the components in this XYZ frame. So if we have X, Y, Z, U, theta, and phi, we should first compute the true anomaly, which is only depending, given these quantities, only on X, on the coordinate X, the radial one. Okay. Remember that you can invert, you can get A and E from inverting these expressions. These are very easy to invert. So you can go back to the angular elements in this way. Just considering the X coordinate, you get the cosine of F, and the sine you can get from the sine of F. You can get it from the sine of phi for the consideration done before. Then the next thing is to use Z to compute small omega, because you now already have F, so you have the argument of the latitude from this expression, and you can choose the quadrant of the argument of latitude and thus of small omega by using this expression. And finally, we use the coordinate y to find the longitude. So we are able to go back and forth. This is a complete set of transformations. It's a bit boring. It's very simple. The computations are all very simple. Now let's try to look deeper in what are the geometrical meaning of these coordinates that we are introducing. And to do that, okay, let me skip how you derive it. This is in the paper of 2003. But basically, we consider what is the minimum of the distance of the straight line describing the motion of the small body from the y-axis. It's very easy to set up the equations and to solve for the derivative with respect to a variable involving y, and then find the value of the coordinates that, given the sine and the cosine of phi, would give you the point in which the trajectory is closest. And this is the MOID in this theory. So it's an approximate value, it's not the MOID of Giovanni B. It's much easier to compute. So it's the only good point it has. And actually, the formula that I give you here is a generalization of what was given in the paper of 2003, in which this part was missing. Okay. Then, since we are able to follow the motion in time, given that we have stipulated that it's just a rectilinear and uniform motion, we can play again the same minimization game and find the instant in which the small body crosses the B plane. Because this is something that up to this moment we had not yet computed. We had only the parameters at some time T star, but we didn't know when we crossed the B plane. We need this, and this is the computation again using the rectilinear and uniform motion to find it. So at this point we are in the position to explicitly compute the coordinates of the small body in the XYZ frame in the instant in which it crosses the B plane. This is one thing we wanted to be able to go on. So the next thing we do, we then introduce the B plane frame. The B plane frame is a frame such that the B plane is composed by the plane of the coordinate xi and zeta, and the eta axis is in the direction of u, of the motion of the small body. Why this strange way of defining? Well, because it was already present in literature, a paper by Carusi, Greenberg, and myself, in which we had defined it such that the xi, eta, zeta frame coincided with the XYZ frame if both theta and phi were 0. So that's the simple historical reason for describing it like that. And we can set up the coordinate, we can compute the transformation of the coordinates in that frame for the generic point we had at the beginning and for the coordinates at the time of the cross. So finally, what we are really interested in order to be able to do our charting is to have these coordinates xi and zeta, which are the components of the vector B, that has a magnitude given, of course, by this formula. Now, we have just demonstrated before, without realizing, that xi corresponds to the local MOID, because if you notice, this is the definition of the local MOID with sign that we gave a minute ago. So, these coordinates turn out to be quite useful, because the horizontal coordinate, the xi coordinate, is the local MOID, and so it depends basically only on the orbit geometry, on how the orbit of the small body behaves in the vicinity of the orbit of the Earth, and there is no information on time. All the information on time goes into zeta. Okay, so we have decoupled, so to speak, the fact that the small body can arrive late or early from how far are the orbits from one another. This is different from the way in which Chodas was doing his plots. Oh, sorry. In this case, the plane is the same. But if you are asked what is the MOID, well, the MOID must be something orthogonal to this and in that direction. But then you would ask immediately, why not use it as a coordinate? Because then the time difference will go in the other direction, much easier. So this is a reason to adopt our reference frame, which is more convenient from this point of view. So. And at this point, of course, we are also able, since we were able to introduce xi, eta, zeta from x star, y star, z star, we are also able to do the opposite. And so in the end, yes, okay, this is the summary of all this. So I have shown equations that allow you to go from AEI, small omega, capital omega, and F star at time t star, when the small body is near the planet, and from them to compute the components in this XYZ frame. Okay, first step. Second step, we are able to pass from this frame to the coordinates in the epic set, I would say. So these three coordinates tied to the velocity, and these two coordinates on the B plane, and the time of encounter. So we are able to go this way, but then we are also able to do all the inverse steps. So we have three completely three descriptions of the same thing in three different systems: the orbital elements, XYZ space, and the B-plane frame, and we are able to shift from one to the other, and we will exploit this in order to help our understanding of what is going on as a consequence of the close encounter. Okay? Okay. So, now we have set up everything we need to describe the encounter. Let's see what happens at the encounter. So, as I said before, at the time of the B-plane crossing, which is denoted as TB, and we know how to compute it, we rotate the velocity vector by an angle. Let's call gamma this angle, and we rotate it from being parallel to the incoming asymptote of the planetocentric hyperbola to becoming parallel to the outgoing asymptote. And we correspondingly shift the position of the small body from the one corresponding to the minimum encounter, to the minimum distance on the B-plane pre-encounter, to the corresponding B-plane that is normal to the outgoing asymptote. Okay? So, in practice, this means that we want to pass from the x, eta, zeta, remember eta is 0, coordinates on the B-plane frame. We want to know where the particle should be put in order to lie on the B-plane that is orthogonal to the outgoing asymptote. And to do that, we have to apply this rotation. The xi coordinate rotated becomes xi cosine gamma, the z coordinate becomes zeta cosine gamma, and now in the new B-plane, the eta coordinate with respect to the first B-plane is not 0 anymore, it's b sine gamma. Okay, it's just simple rotation geometry. Now, to be able to go on, we introduce some quantities to simplify things. The first quantity we introduce is called c, and is the mass of the planet in units of the mass of the sun, divided by the square of the velocity, the planetocentric velocity. Why do we do that? Well, basically because the formula that I have forgotten to write, sorry, is that the basic formula which was introduced by Epic, by the way, is that the tangent of gamma halves, gamma is the rotation of the new vector induced by the encounter, is c over b. You can using c is just c over b, where b is the impact parameter. This means that you can interpret c as the distance at which the small body has to pass from the planet on the B plane in order to have the velocity vector rotated by 90 degrees. Okay, so it's a characteristic length. And since it depends on the mass of the planet, which is an invariant, and on u, which is also an invariant of the motion because of the conservation of the Tisserand parameter, c is a characteristic length that you can compute for every NEA. In practice, for the majority of NEAs, this quantity is something smaller than the radius of the Earth. For instance, we will discuss later in the second lecture the dynamics of the body that was mentioned by by Andrea 2009 FD, which is a typical NEA encountering the Earth. This NEA has an encounter velocity of about 15 kilometers per second with respect to the Earth. And this velocity in units of the Earth's velocity is 0.5. Its square is 0.25. And if you compute what is this the distance at which it should pass from the Earth to turn the body by 90 degrees, you get something like 1/10 of an Earth radius. So in practice, you can interpret this information by inverting it. You can say that the majority of the NEAs travel so fast with respect to the Earth that it's very rare that they undergo a close encounter in which the velocity vector is rotated by 90 degrees. Well, it's impossible for the majority of them. Let's say it's rare already to have a deviation by 10 or 20 degrees. It happens from time to time. Apophis will have such a rotation, but it's really an event. Okay, so starting from that, from the expression that I mentioned before for the gamma, we can compute these quantities in this way, and so express the rotated coordinates in the D-plane frame in this way. We can do all the math and compute what are the new components of the B vector rotated after the encounter. You get these expressions that are all, you notice that there is nothing unknown now, because everything is function of something we have already defined and computed. And we can also compute the rotated components of the velocity vector, which is what we need to compute the new A, E, and I post-encounter. And again, you will notice that there is nothing that we already don't, or which we don't know the vector. So we can define a post-encounter D-plane, which that is characterized by the angles phi prime and theta prime, and we will have on this new B-plane these rotated coordinates. And again, just as a check on the computation, you can be sure that also in eta prime will also be 0. Now, the interesting thing to remember is that xi prime will be the new local moid, because there is no guarantee in general that the moid after the encounter is the same as before. In most cases it is like that, but it's not guaranteed. And we have an explicit expression for it. And then, having done all this rotation, we can compute the rest of the motion, which will be again rectilinear, yes. And why to do that? Well, there is a use of this formula, because suppose that we have defined the pre-encounter state by taking the instant at which the small body crosses the ecliptic. So T star was corresponding to Z equals 0. Now, if we want to then compute what happens to the small body in the revolutions after this encounter, we need to anchor our evolution in time from the corresponding moment after the encounter. So we need to compute T prime star as the time in which Z prime star will be 0. Okay? And the way to compute is from this formula. Otherwise, we would miss the synchronization of the system, so to speak. So, summarizing, all the machinery I have described lets you pass from the pre-encounter components u, theta, phi to the post-encounter components u prime, which is equal to u, theta prime, and phi prime, through these explicit expressions that are functions either of t and are functions of t, phi, and xi and zeta. Okay, so it's a complete description. And we have also the post-encounter epic variables, xi prime, z prime, and t prime star, whatever the definition we have decided to adopt for it, which are also given by this simple formula. And remember, this is the new local moid, And we have this interesting transformation law for the moid. So the new local moid will be the previous moid multiplied by the ratio between the sine theta divided by sine theta prime. So if theta doesn't change, for instance, the moid will not change. Or if theta changes only by a few degrees, the new moid will be practically almost identical to the first one, to the previous one. Perhaps I should stop here, and because then we go on with different subjects. This was the worst part. Later is if you have some quick questions.
I lost you at some point. So there is psi r and psi prime, for example, and eta and theta. So there are three.
Xi is the coordinate which corresponds to the local moid on the pre-encounter B plane.
Okay.
When you apply the rotation,
okay,
but still keep the same reference frame,
right,
the new point, the rotated point, must be Xi R.
R. Okay.
So R is called rotated, and the same for the other coordinates. Then, once you have rotated, you introduce the new B plane, and you will have a new set Xi prime, zeta prime. Okay, the eta and Xi prime is that.
So that means that eta prime is 0.
Yes, exactly.
Okay.
I have two short questions there. One is the plot with the impact irradiance. There was one pattern that I saw in there, yes, that I'm curious about,
yes,
whether my interpretation is correct. Because of the way you described it being day and night, I'm assuming that the bias that I see is leading edge versus trailing edge.
Yes.
Because you see more density of points, and I guess I'm hoping it's not an optical illusion, but it looks like on the right half you have more impactors than you do on the left half. And even on
yes,
the night side, you have more on the right side than on the left side. Is that an artifact of?
That depends on the population. That depends on the population.
Yeah.
This is done with the population. This is the population of impactors that was extracted from the reference, what has been the reference population, model population done by Botkin, Morbidelli, Jellicky. There is a famous paper in which they built an enormous machinery to debias and compute the evolutions from the source regions and so on and so forth. And so they got a population of near Earth asters. Now, when you have a population of near Earth asters, not necessarily all of them can be impactors. In general, not. So what Chesley and Spa produced this population did was to extract from this original population those that allowed an encounter with the Earth. And so they produced a list of about 5,000 such impactors. Now, I have taken that list, and each of those entry lines has a specific value of small omega and capital omega. Okay, capital omega doesn't enter in the problem because of the rotational symmetry with the circular orthogonal. What I did is I took away small omega and computed the 4 values of small omega that correspond to exact crossing with the Earth. And if you notice, every point enters 4 times in this plot because it can enter 4 times in its small omega cycle. And the 4 times correspond to post-perihelion ascending node, post-perihelion descending node, pre-perihelion ascending, descending. You would see the symmetry if I rotated this plot by 90 degrees, which is actually how originally it is made, and it is done for meteors. For meteors, it's not centered on the opposition, because the opposition doesn't mean very much, but is centered on the apex of the Earth motion, the direction of the Earth motion. If you do that, okay, the plot deforms but becomes symmetrical, and in that case, this quadrant corresponds to descending node, the night side, which is exactly when you observe meteors in the northern hemisphere. And it's the most populated just because most of the observers are in the northern hemisphere, and you don't observe usually the other hemisphere, the hemisphere.
So it's an observational artifact in some sense.
For the meteors. In this case, it's not. In this case, it's not. The majority of the impactors in the Chesley spark population taken from the Botkin Morbidelli population have a value of theta. They come slightly from the back. If they came exactly from the side, you would see symmetry around this line.
Okay. This approximated formulation is valid in most cases because I believe the planetocentric velocity is quite high. But there are some cases in which it's not valid.
Yes.
What is the limit of validity for slow encounters?
Already for velocities like that of Apophis, you start to, which is 6 kilometers per second, you start to see some departure. On the other hand, if you take the population of the brightest NEAs, which is complete, we know all of them, there is no observational bias, and then you ask yourself, what is the slowest one? Is Tutatis, which is traveling at 10 kilometers per second, and the average speed is over 20. So, in reality, if you go to the catalog of observed near-Earth asteroids, you will see that it is much shifted towards lower velocity, but this is an observational bias. Because the objects with lower velocity, you can show that have a higher collision probability. Higher collision probability means also higher probability of being discovered.
That's the point. I mean, if you take into account the weight by the probability of collision,
It's slightly different.
Ones.
Well, this is weighted by the probability of collision. I have done this corresponding plot for the unbiased population, and it is much more to the left. They are coming from the front, but they are unfavored by probability. Okay, let us make 5 minutes.